Hello everyone, welcome to Meda's Bridge. We train and learn. We shall continue our embedded system learning. Let's get started. Today's our learning goal would be various architectures in embedded systems. Hi,
Hello.
thanks for joining, sharing our embedded system experiences.
Sure, thanks for inviting me. So we shall continue our exploration on CPUs which we use in embedded systems today. CPU is one of the core component in embedded systems. We all know, right? CPU means central processing unit. So can you elaborate?
Central processing unit built into embedded system that controls the system's basic functions.
That's correct. So now you know the sense of like a CPU and its role in embedded systems. Okay, we have microprocessors, microcontrollers, digital signal processors, FPGA and ASIC, SoC, system on chip. By using these processors, we can build various category of embedded systems in various domains. ASIC means application specific integrated circuit. FPGA means field programmable gate array.
SoC means system on chip. DSP means digital signal processor.
System. You mainly see the basic components like how CPU interacting with like a sensor, how CPU controls the activators. If you look at an embedded system, these are the typical components which we can see. And see sensor. Sensor is basically giving a analog signal to the CPU through the ADC. The ADC means analog to digital converter. What it does, it takes the input from the sensor as an analog signal, convert into a digital signal because CPU only needs a digital signal to understand. CPU probably process the signal as per the algorithm and then put the resultant value in its RAM or the memory. For instance, we have various memories which we use in embedded system. For instance, here RAM, ROM, flash are widely used memories. There are various other type of memories which we can talk later. The next part would be CPU will communicate to the activators through the DAC. Activators may be only understanding analog signals. So CPU takes the data from the memory and feeding that into the DAC circuit. DAC means digital to analog converter. So which converts the analog digital signal into analog and then analog signal now giving as an input to the activator. In embedded system, we require an interfaces like an IO ports and communication interfaces like RS-232, Ethernet, RFID, CAN, USB, things like that. For the entire system to design, what we require is a power supply. So designing a power supply unit in embedded system is one of the critical component which we need to understand. Similarly, we have a timers, interrupt controllers which we use in embedded system. Basically, these are very essential for us to build in algorithms when we are interacting with external interfaces.
Yes, of course. Understanding the interplay between these components is crucial for designing, developing, and maintaining effective embedded devices.
Very good. Thanks for adding. Let's look at the overview of the processor architectures which we use in embedded systems. In embedded system, we have two types of processor architectures based out of the instruction set of the processor. We have a CISC and a RISC. CISC means a complex instruction set computing. RISC means reduced instruction set computing. For instance, Intel x86, Motorola 680K processors are a CISC based processors, whereas analog DSP, Texas DSP are considered as a RISC processors. Let's look at the few important features of each type of architecture.
The differentiations in CISC are hardware centric design and number of instructions extended to approx 100 to 200.
So basically, when you say complex instruction set, means CISC has hardware centric design. That means like the instruction sets are pretty high, then you have to think through how you can design your hardware. Instruction sets are complex in type and variable in length. So this is one of the challenge when you are developer writing a code on CISC processors. Instructions need a multiple of clock cycles for executions. You can make an important note out of this statement. There are various addressing modes which we use in the CISC. The register sets which we use in your algorithm, right? The availability of register set is very less in CISC. So the code size, code means the development source code size would be large when we are working on a CISC type of architectures. Instructions accessing memory is also limited. We have load and store are the instructions which we widely use in CISC. CISC was developed to make compiler development simpler. Okay, can you share something on RISC as well?
Of course, coming to RISC, the software centered design. It is number of instructions are reduced and it has small number of fixed length instructions and it limited addressing modes having multiple register sets. In this, code size is small and instruction execution is in parallel, which is pipeline, we say maybe. Almost all instructions supports to access memory. Development of RISC compiler involves complexity.
That's very good. So RISC basically total design incorporated in hardware. So our thought process always would be on software centric design, and then the number of instructions are also reduced because hardware is taking a full control. So you can use a minimum instructions to write a algorithm, right? So that implied the code size would be small, and then there are the many hardware registers available within this type of architecture, and address modes is also kind of a limited. One important point that we have to reiterate in RISC supports a parallel processing and hence it is faster, and the most of the instructions which we use in the RISC are having an ability to communicate to memory directly. So other way around, all the instructions supports to access the memory. If you look at RISC compilers involves a complexity in development. When you talk about architectures, the first thing that we have to understand is how CPU interacting with memories and IO devices. When you are interacting with the memory, you need to have an address bus to refer the memory location, data bus to fetch the data from the memory location. Similarly, when CPU is sending a data to the IO devices, you mainly needed a data bus. So the takeaways, you need to understand what is meant by data bus, what is meant by address bus, how the CPU interacting with memory and the IO devices. The important observation that you need to understand is in any typical architecture, the CPU when you use a memory, what type of memory it is, and then where your development piece of code go and actually sit. That is important. So let's look at the first type of an architecture.
The Neumann architecture was designed by famous mathematician and physicist John von Neumann in 1945. It designed based on concepts of using single memory space. Program data and instruction data are stored in the same memory. High level of flexibility as the memory is shared between instructions and data. Speed is limited due to only having one memory location and set of buses, typically used in general purpose computers that will be used for many different purposes.
That's good. If you look at this diagram, the CPU uses a single memory space. In this memory space, we have a code and a data together will be stored. What this means is the same memory space is what we are using to share the code and data. If you look at from the CPU standpoint of view, when you are trying to access the memory to fetch the code or to fetch the data, all you are using is just one address bus and then data bus. So you are sharing the buses for accessing both code memory and then data memory, and hence there should be a speed limitation, which we are actually talking about. A speed is limited due to only having one memory location and a set of buses. This type of architecture you widely see in general purpose computers. Let's look at the concept of program memory and data memory, which we use in embedded systems. If you look at this, a sample program, the program means a sequential set of instructions, isn't it? The probability of the logic which you build inside the sequence to perform the particular task. My interest here is how this program gets stored in the memory, and then what would be my differential understanding between program memory and then data memory, right?
As we know, we have two memories, ROM and RAM. In ROM, the whole program gets stored.
That's correct. ROM means read only memory. Once you program it, it will stay. This code will persist there itself. So this also considered as a concept of program memory in our context. The entire code will be stored in the ROM, read only memory, which is what we say a program memory. Whereas
Now look into the variables. The variables will be stored in RAM.
correct, RAM means random access memory, is sort of like a runtime memory. All the variables which we create would be storing in RAM, and hence we can call them as a data memory, because this is a data, right? The variables are going to store the value of the data, right? So and hence we require a data memory for storing the values. So now you know the concept of a program memory and data memory which we use in embedded architecture.
Yes, of course. As we are seeing is a physical notation of the program which is stored in the memory.
That's correct. Instructions execution life cycle. Let's look at a CPU is trying to execute the one of the instructions from your program. Let's say C equal to A plus B. How this will be done in your processor, isn't it, right? So what CPU would do first? CPU try to locate the program code area to fetch the instruction. So first thing that it has to be done, fetch the instruction from the program memory. Let's say it fetch the instruction. The next thing would be CPU is trying to decode the instruction. Decoding means understanding what that instruction mean and then what CPU should do with that instruction. Let's say CPU determines the operation to be performed. While looking at the operation, it also determines what are the operands that are required to perform that particular operation. In our case, C is equal to A plus B, right? Plus is an operator. It requires two operands. These operands will be available in your data memory, right? So CPU is trying to fetch the operands from the data memory area. Now that the CPU has operation and then operands, so it executes it, compute the results. The results is now storing back to memory because C is also part of your data area, isn't it, right? So store the results back to memory. That's what the CPU do. With that, the instruction execution for that a specific line is completed. What it will do, it will repeats for all the instructions until the control goes to the end of the program. This is a typical execution life cycle of any instruction on your processor.
Harvard computer architecture design is based on concept where there are separate storage and separate buses, signal path for instructions and data. Here we have two separate memories, program memory, data memory. The address buses are separate and data bus are separate. Two sets of memory and buses mean data can be handled more quickly, which would result in decreasing execution time.
Let's look at a super Harvard architecture. We have seen Harvard architecture in which we have a CPU, we have a dedicated memory for the program memory and then data memory, and then we have the IO controller. This remains as is. But what is the new that we can see in super Harvard architecture?
We have instruction cache.
That's correct. Instruction cache is a expensive one which is very near to the CPU, which we use for storing the repeated instruction fetches.
Program memory is for instructions and secondary data.
That is correct. Here in the program memory, we store a complete program and also a one-time configured data, which we are going to persist for entire program. Whereas data memory, which we use for storing the runtime variable data. Let me share few pointers on ARM architecture. ARM architecture is widely used in today's embedded system design.
ARM processor is designed with combination of RISC and CISC features, which are well suited for embedded system design. And features are multiprocessing, one cycle execution, pipelining, large number of registers, and faster execution, and so on.
Very nice. Thanks for sharing. In ARM, we have a various versions and then associated families. You can see today's widely used one of the ARM processor is Cortex. What I should have to consider while selecting a processor for embedded system design?
Based on performance, based on specialized processing units, based on power drawn, based on memory, based on peripherals, based on operating voltage, based on cost consideration.
Thank you.
Thanks for watching. Please like, share, subscribe, click on the bell icon and please leave the comment. Happy learning. Thank you. Stay tuned to the upcoming sessions.